Harvey grew up in North Dakota. At the age of 8, he started doing simple experiments on gravity in the basement of their home. He graduated with a master's degree in electrical engineering from the California Institute of Technology in 1959. He also has a minor degree in artificial intelligence. He worked on gravity research at Caltech and at Hughes Aircraft. He's worked on missile guidance systems and on the Surveyor spacecraft, the Apollo, and the Space Shuttle. He also worked on various Space Defense Initiative programs, SDI. He married Bonnie Kiefer in 1957, and I think she's here. Yeah, right up there. Cool. And Bonnie graduated from the North Dakota State University with a Bachelor of Science degree in Home Economics.
Yeah, is this for me?
Harvey and Bonnie live in Downey, California. They have 10 children and 24 grandchildren. I think 3 of their children are here today, if I'm not mistaken. Yeah, there's 2 of them. There's one more right there. Okay. And Harvey retired in 1992, and now he's busier than ever working on inertial propulsion. And that's the subject of our presentation today.
Thank you, Mike. Want to make, you can hear me all? Okay. Well, first off, I'd like to say that it's a great privilege to be able to talk to an audience like this, and I want to compliment the Tesla Foundation and Steve Elswick and all of his staff. I know it takes a lot to put something like this on, and at times it may not be very rewarding, and so I realize and appreciate the opportunity here. And I guess Mike mentioned my family here, but I want to mention that there are 7 members of my family here. My wife, Bonnie, and my son, John. Obviously, I want to give him a lot of credit. You know, sometimes he gets 3 hours of sleep in 2 days or something like that, and I just had him, I forgot my script at home, so I just had him write it in this last hour here, see. And his wife is here, Patricia. She's operating a video camera today, and their son, John Arthur, is here manning the floodlight. And my daughter, Marie Claire, is here, and my son James is here. And I'd like to mention that last year we had 6 people here from my family. My son Andrew was here, and I mentioned all the people, and I forgot to mention that Andrew was here. I'm sure that didn't sit too well with him. And so this is the 3rd time. There's 3 generations in my family here, John and his wife and son and myself, and for about 3 meetings at the INE before this, Institute for New Energy, we had 3 generations there, and I used to go alone for some years prior to that to Hal Fox's meetings over there. And someone told me that every good speaker should have at least 1 good joke and drop at least 1 big name. So here's my joke. This beautiful blonde was driving her car, and it was about a 50-mile-an-hour speed limit, and she was doing about 80 or something like that, and the policeman pulled her over, and it turns out the policeman was a beautiful blonde also, policewoman, and she came up to the window, and the lady rolled the window down and says, "May I have your driver's license, please?" And so the lady in the car starts looking for it and looks in the glove compartment, can't find it, and she says, "I'm sorry, I can't find it. Could you tell me what it looks like?" And so the patrolwoman said, "Well, it's about the size of a credit card, and it's got your picture on it." So she starts fumbling around again, and in her purse she found the little mirror for her makeup kit. And she looked at it, and okay, she handed it to the lady. And the lady looked at it and seemed puzzled for a moment, and she handed it back, and she said, "You're free to go. I didn't realize you were a cop." Now let's see if I can figure this thing out. Where do I point this?
That's page back, that's page 4.
Okay, page 4. You make it move the first time.
You try it now. It is. There you go.
Okay. Now I'm going to advance.
And here's your laser.
Thank you. Now, I saw this in the paper the other day. It shows Arnold Schwarzenegger, our famous governor in California, in an electric car by Tesla Motors, Inc. And I assume that Tesla Motors is just a subsidiary of the Tesla Institute here, one of Steve Elswick's subsidiaries. Not really, but anyhow, I thought that, and it goes 250 miles before its batteries need a recharge, Tesla said. So that's interesting. And now I'm going to drop my one big name and get that out of the way. There's Stephen Hawking. How many of you know Stephen Hawking or who he is? He's probably one of the most prominent physicists alive today. And I'll show you a few more. Here's his picture today. He was diagnosed after getting his PhD and getting married and have a family with 3 children. He contracted Lou Gehrig's disease, maybe also called ALS or something like that. And here's another close-up of him. And he met with Pope Paul in 1981, just getting that out of the way. And the reason I'm talking about him is because I attended one of his lectures a month ago. And it's not easy to attend one of his lectures. At Caltech, which is my alma mater, he spends one month in the summer each month here, and the rest of his time is at Cambridge. And and he spoke, and there's a project at Caltech called the Einstein Papers Project, and it has 4 editors, and they're documenting all of Albert Einstein's technical memos, all of his correspondence, his love letters too, and the love letters received, which really shed new light. They try to keep that undercover for generations, and they did until about 10 years ago it broke out. And only the staff and students could attend, and so I know one of the 4 editors quite well on this project, and his wife was in Hungary, their home, so he gave me a ticket, and I attended, and the line was at least 1/8 of a mile long, and they had, big auditorium and 2 overflow facilities and I wanted to ask him a question. I rather simple-mindedly thought that, they'll ask questions, and I'd raise my hand and say, Dr. Hawkins, you're the inventor of the Big Bang Theory, And the Big Bang Theory says that at some point in the past, there was essentially nothing, and suddenly a big bang, and in like 100th of a second, all the matter in the universe was out in place, actually expanding a little, apparently. And then I said, on the other hand, Einstein's theory of relativity says that nothing can travel faster than the speed of light. And so, however, now you're the greatest physicist, and you say the Big Bang Theory, bang, everything traveled out at practically an infinite speed. But now, in the next breath, you say nothing can travel faster than the speed of light. How do you reconcile those two? That's an interesting question, and I'm not blaming him for limiting things to the speed of light, but I thought he would be a good one to comment on it. And so at the end of his session, they entertained questions, except, he's not that adept at answering. He has a little computer and a little monitor, and he pushes a button and the alphabet scrolls in front. When he wants a word that starts with B, he stops on a B, and it puts out all the words that he's used to it, and he picks those words, and then it puts it out in a computer voice as close to him. And so he asked 5 questions, but he had the campus ask the students to present 5 questions, and the evening before, they called out 5 of the best questions and gave them to him, and he prepared his responses like this. And actually, it's a little bit sad in his. Let's see here if I can. It's a moving experience to see him. Let's see, what was I going to say? Yeah, he's paralyzed, like from the neck down, and he can turn his head only about 10 degrees in each direction, and he can move his fingers. That's it. And he believes in God because he says there's no other way he could be alive at this stage. 40 years ago, they thought his time was up. And so I did not get to ask him that question. But as they wheeled him out, he has a personal attendant. As they wheeled him out, I realized I wrote the question out on a 3x5 card and I handed it to his caretaker. But if anyone could explain how the universe could be created from a big bang and not traveling at greater than the speed of light, then I want them to let me know. Now, I mentioned the speed of light here. Because my understanding of the speed of light is that man cannot perceive anything to be traveling faster than the speed of light. And the reason for that is because whenever you measure the distance to something or its speed, it's with radio waves by radar or with LADAR, laser. It's with light beams, electromagnetic radiation. And those travel only at the speed of light. Now you tell me, if something is traveling at twice the speed of light, how are you going to measure its distance or its speed with something that can't keep up with it? It's not possible. And so I maintain really that matter can easily travel faster than the speed of light. And I'll give you some examples that if an airplane, there's a real speed of sound. If an airplane approaches that, they do hit a barrier, but if they're smart enough to go through it, they proceed through it. And our planes have gone Mach 10 and Mach 12. Okay, with the speed of light, if we're in a little spaceship here, if you and I were in a spaceship and we somehow had an inertial propulsion unit, which is what I'm talking about now, if it could accelerate our little vehicle at 1 G, then it would 1 G continuously. Now this would rely on some of you guys to supply energy to it. We need some zero-point energy process feeding it, feeding an electrical generator which powers the inertial propulsion unit. And I am really predicting that within a decade or so there will be ZPE and inertial propulsion which can produce sustained acceleration. It'll be a marriage of the two, and then you can have this spaceship. Right now, the theories of going to another planet, using solar sails and getting up to 2/3 the speed of light, that it'd take you 100 years to get there, and if due to this time dilation you somehow lived and you somehow came back, your wife and your family and your grandchildren, all that would be long gone. And that's all, forgive the expression, that's all horse pucky. And now if you and I were in a spaceship and accelerating at 1 G, pretty soon, within a couple of years, we would approach the speed of light. And we know our speed because we know the acceleration that we're traveling with, and we can calculate our velocity and our distance with the equation. We integrate the acceleration to get velocity, we integrate the velocity to get time, and we could say, hey, we're about to pass the speed of light. Do you feel anything strange? No. The truth is you look out the windows, nothing's going to happen. and you say, well, by golly, we're exceeding the speed of light now. And according according to my calculations here, let's see, light travels at 186,000 miles per second, and I think I need to go to, now I'll start relying on my medium here. Whoops. Well, basically, I have a hard time reading that from here, but it'll take about 2 years to get to the speed of light. And when you get to the midpoint between here and Alpha Centauri, then you have to start slow down, so you just turn your vehicle around or reverse the IPU. Then you got to slow down so you don't zip past Alpha Centauri at 4 times the speed of light. And then you'll spend a year in orbit around Alpha Centauri, taking data and so forth. Then you point yourself back toward our solar system and accelerate again. Again, you'll pass the speed of light, and you get up to about 2 times the speed of light. Then you start slowing down. And at that point in time, let's see here. Anyhow, the total time, 4 years up, a year in orbit, 4 years back, takes about 9 years, and your wife and your kids will still be there waiting for you. And if you could travel at 2 Gs, which right now 1 G is how much force holds us to the Earth. If there was 2 Gs, you'd feel kind of heavy. You'd feel kind of heavy, but if you traveled at acceleration of 2 Gs, you'd cut it down to 5 years. And those are real numbers that I absolutely believe in. And I can't prove for 100% sure that man has the capability to achieve inertial propulsion, but I believe so, that it'd be premature for the world to end without reaching that goal. And we're just on the beginning of exploring the whole universe, and our knowledge is exploding at such a tremendous rate that I believe that we will travel to the stars within, probably not within our lifetime, but within our lifetimes of our grandchildren, for sure. Now, how many of you have seen this website, the NASA Breakthrough Propulsion Physics Project and Common Errors? Any of you familiar with that at all? It's a very, very good website, but I'm going to give you the good news and the bad news. The good news is that, well, I'll go ahead and read this one thing. A variety of breakthrough propulsion ideas are regularly submitted to NASA Breakthrough Propulsion Physics Project from amateur researchers, far more than can be assessed. Many of these submissions involve concepts that are already known to not work, even though detailed assessments have not yet been published. Here now, as a service to other would-be submitters and other curious researchers, are examples of commonly submitted ideas that are not propulsion breakthroughs. These examples include a description of why they appear to be a breakthrough and a description of what they really are. And commonly submitted concepts, they break them into 3 groups: oscillation thrusters, gyroscopic anti-gravity, which is it should call it gyroscopic thrusters if they want. It's not really anti-gravity. In the electrostatic anti-gravity. And just a moment. Okay, to develop inertial propulsion and have good communication between scientists, you have to have a good definition of terms. And I'm reminded of, like in the electrical engineering, a lot of people, experimenters, they don't really know what a volt is or an ampere or an ohm, resistance, capacitance, inductance. reactive power and real power, they don't really understand those terms. They use the word juice a lot for it. Well, I got to give it more juice or something, you know. And you will never make a great breakthrough unless it's serendipitously and just God allows you to stumble onto the solution. That happens, but it's not something you can count on. And this reminds me that last year, here I presented a paper on how to correctly measure electrical power and to avoid pitfalls. And that paper was published in their magazine here. And 3 or 4 months later, I got a couple of phone calls from people. There's one young researcher, he had a 3-phase transformer. And he said he found out that if you can put 3 loads on it, a 3-phase loader, you can put 3 independent loads. He found out that when he left one of the 3 phases unloaded, he got more power out of the other 2 than he put in. Well, that's because he was measuring voltage and amperes independently without considering the power factor. And that's an example of, I'm glad my lecture last year did some good. And even more so, when we're trying to develop inertial propulsion, we need absolute communication. We have to understand things like, I define the active mass in the case of gyroscopic stuff. I have a rotor spinning. Anything that's spinning is called active mass. The housing, the frame, the cabin, the payload, all that is called passive mass. And the ether, there has to be an ether. And remember from the last one, there was a bar magnet with all the flux lines. Okay, those flux lines can't exist if there's not an ether. Nothing can exist. In fact, my son John here had this demonstration, a little magnet and a non-magnetic tube. And if you drop it in, first I'll drop it like that. That was 1G. Now if you drop it like this, okay, that couldn't happen if there was not an ether. If there was not an ether, it would fall straight through quickly. On the other hand, if it was not there, every single atom in the universe depends on it exists within the ether. If the ether didn't exist, the atoms wouldn't exist. The ether is the structure upon which all things are built. Angular momentum. That's a very, very big term in inertial propulsion. I won't go into the definitions of them. And torque. A lot of people don't know the real units on torque and force and angular momentum and so forth. You have to understand stuff like that. And centrifugal force, conservation of angular momentum. It appears, the establishment scientists think that conservation of angular momentum rules out everything that I'm going to be saying, and it's dead wrong. Dragging of inertial reference frame. Every object, and especially every rotating object, they have their own local inertial reference frame around them. There's a universal inertial reference frame, which is the whole universe, and it's basically fixed. Our solar system has its own rotating inertial reference frame. An electric motor has its own inertial reference frame. And energy density, energy momentum tensor. Now, the real scientific groups, to break through, they're going to have to understand the energy momentum tensor. And 99.9% of people say, what's that? A flywheel. Now, I take issue, if you have a spinning rotor, everyone calls it a gyroscope. It's a rotor. A gyroscope is something far more sophisticated. The word scope implies something more sophisticated. There's fiber optic gyroscopes, and a rotor is a rotor. It's a flywheel. Force, that's an important term. And force precession, I'm going to move on to friction. In that first category of oscillation thrusters, if it's something resting on a surface, it really works by friction. If if you jerk something real fast, it'll overcome the kinetic friction and move forward. And then if you back it up slowly, it won't move because it can't overcome the static friction. Then if you jerk it forward again, you'll move again. Then if you move it back slowly, and a lot of those things, except some of them don't sit on a surface, some float in water, and some work in air. And I've studied a lot of those, and I have the term nonlinear response to a viscous medium. There's ones that work in a lake, in water, and it actually moves forward. And it's because the atmospheric drag, for example, on something moving through the atmosphere, the resistance is proportional to the square of the velocity. And if you move forward fast and back slowly, you'll end up with a net movement. And if it's not sitting on a hard surface where friction is involved, I call it nonlinear response to a viscous medium. And I can analyze and show why things won't work. Gravitational potential, gravitational constant, that's simple. They say that is slowly changing with the universe expanding. Gravitational potential, that needs to be understood. Now, about 10 years ago, the scientists started to loosen up a little bit. They recognized that there is a gravitoelectric field. I show some of the references. And there's a gravitomagnetic field, and there's gravitomagnetism, and there's plain old gravity, and more terms that have to be understood to be able to hover or levitate. I'll back up a second here. Hurrying torque is something where if you have a little toy thing going round and round, and you torque it, increase it'll move up. That's called a hurrying torque. If you actually slow it down, that's called a slowing torque. That's okay. The graviton. We can't really say that there is a graviton, but it's a hypothetical particle that meets a lot of conditions, and more power to them. My instructor, Dr. Feynman, was one who tried to quantize gravity, and he never really succeeded, but he helped establish the properties of a graviton if it existed. It seems like inertial reference frame, I've already talked about those a little bit. Kinematics and moments, just mass. When I got to this point, I realized that there's too many terms, and I shouldn't spend this kind of time on that stuff. So, and Newton's laws of motion, a person should understand those for sure. And my understanding of none of this stuff violates Newton's laws of motion if you consider them in a broader context. Right now, they consider them only in X, Y, and Z, and time. If you consider them in a broader context, which really considers the ether, then they apply, his laws are exactly true in all respects. I won't go through those. Here's an interesting thing. In the mid-1960s, a jerk effect, the time rate of change of acceleration was hypothesized as a new type of force, but no experiments, no physical evidence were ever offered to demonstrate that such a jerk exists. And even if it did, whether it could be used to create a space drive. Now, that's a little bit of bunk there. They're talking about that a jerk as a time rate of change of acceleration, that there's no examples of it existing. And that is not true. I worked on, I'll say, the Star Wars programs. And if you have a rocket, let's say a rocket accelerates at 5 Gs. When you turn the motor on and the blasts out, the acceleration goes from 0 up to a value. And the time rate of acceleration, if it takes 2 seconds to get up, the time rate of change of acceleration, that's defined technically as a jerk. There's another term for it also. And then if you shut the motor off, or if it runs out of fuel, Suddenly it goes from 5 Gs down to 0 Gs. During that time, there's a negative spike, a reverse jerk. And of course, I'm not saying that because there is a jerk that it can be used as a space drive. I'm definitely not saying that. I think that let's see. A lot of people talk about converting rotary motion to a linear thrust. And really, what this says is true. He calls them oscillation thrusters. That's a good term. They either work on nonlinear response to a viscous medium or on the friction. Friction is also considered a nonlinear medium. And also, now if a person could develop an inertial propulsion unit using a nonlinear response to a viscous medium where the viscous medium is the ether, man, that would be the living end of everything. That would do it. But so far we don't know how to interact very much with the ether. And here's a case where lathe weight, there's a 50-pound mass on a 3 or 4 foot pole, and a lathe weight can barely pick up the 50-pound mass. And he took a little motor and he spun it up to about 3,000 RPM, and he picked up the handle and he started turning it like this a little. He started turning it like this and overhead, and he gets as high as he can. 50 pounds went up, and all he was really lifting was the 3-pound rod that holds that. The weight actually disappeared. Now this is something for you to think about. If normally, if you're torquing something, it'll precess upward, and it'll trace out a hemisphere, the upper half of a sphere, and to go further than one lever arm or radius, to go further, you would have to take a step up and repeat the thing. Take a step up and repeat the thing. Once you stop torquing it, it would get its weight and it would fall down, which you want to avoid. And so, but in principle, if you can torque it, have a housing with inertial reference platform in it, and it can torque this thing, and really the big weight is lost its weight, and all you have to do is raise up the housing and the rod that holds it. Let's just say that the 50-pound weight and the 3-pound rod, all you have to do is raise the 3-pound rod. You could put a small rocket on there and raise the rocket up so that instead of tracing out a hemisphere, you'd trace out a cylinder, and as long as you can keep raising it up, you'd keep raising it up. And so you've reduced the problem from using the principle of a precession losing its weight. You've reduced the problem of traveling to the stars. You only have to accelerate a smaller thing, but you still have a propellant, and we're trying to avoid that completely. This is he calls it a lathe weight thing. Here, if this is going round and round, and if you torque it, then those things will rise up. They would rise up, and the most they can go is 90 degrees each, and so that traces out their path will be on a hemisphere. And if you could raise this up, then you could trace out a cylinder and go all the way up. Conclusion about gyroscopic. Gyroscopes can never be used to push a spacecraft, and these are my words, wrong. They cannot accelerate a spacecraft, but they can provide push, as in motion only. But the gyroscopes in the form of reaction wheels can be used to change the angular orientation of a spacecraft. Changing the linear momentum of an object, accelerating it without exerting force on an outside mass, goes against the fundamental laws of conservation of momentum. That's true. But there's fallacies in there, and they don't define their terms. Like push, if I push something, I apply a force to it, and it'll move with its own momentum. If I continue to push it, I'm applying a force and accelerating it. And this allows only for the, without a sustained acceleration. That's true without a sustained acceleration, but the term push is not a good term to use. And that's, now the other thing is on the, looking back on the breakthrough in propulsion physics, it was written by a summer student. And that's NASA's way of slapping the face of all the researchers here who are trying to do propulsion. They're saying that, hey, this summer student, knows better than all of the scientists out there who are working on the problem. And that was a slam, a low blow. And however, PhDs actually wrote the words for it, and it's a negative reflection on them to have as many errors in it as they did have. I would not allow something like that to be written myself, and I would define the terms properly so there would be no question about it. Here's a simple picture of a rotating wheel, and just due to gravity pulling down on it and the supporting it here, that causes a torque, and its response will be it'll go round and round and round, and there's no work being done. Gravity is a constant force. There's no work being done, and you notice that, and in this case it weighs 6 pounds and it's moving 180 degrees. If you stopped it at that point, if you somehow stopped it, it has moved 24 inches from there over to here. Now, in electrical engineering, if you have a sine wave and you want to convert it to DC, you rectify the top halves and you rectify the lower half and invert it, and you fill it in. Now, this is not a real good analogy, but it moved over to here and now it's going to move back, and so you're back where you started. You haven't gained anything. But one simple minor approach is to rectify this motion here and repeat it, and then move it over to here again and over to here again. And my son John and I, 10 years ago, we did this. We had to move over here and fix the, actually, here's the lever arm. Suppose we have another lever arm going out this side, but it's going to move like this. And when it gets here, there's another lever arm out here and another pivot point here. And if the pivot point is fixed such that when it comes here, it can't go further. In fact, it falls off this one, and it starts going like this. And it creates an S-shaped curve, and it can... Now, you'd say, well, it's got these pivot points. They're like a railroad track, but it's not propelling itself by exerting a force against the pivot points. The only force on the pivot point is the weight of the gyro and the lever arm. And now that's a very simple-minded approach using an S-curve, and it's going to move that mass all the time. And that demonstrates, the physicists say that no system can shift its center of mass unless an external force is applied to it. And here's a case where it violates that. And I'm calling this MMD, motion by mass displacement, MMD. And if the scientists say that you cannot have MMD because it violates the Newton's laws, well, that's not true. And I've just proved it here. You can prove it other ways also. But if it is false in saying this can't happen, which it can, then it's also cannot be used to say that sustained acceleration cannot be achieved. Because if it's false for this simple case, you cannot say that it will be true for a more complex case. Okay, here's another comment by this website, the Breakthrough Propulsion Physics, which is slamming the scientists. And it says, for those who are familiar with high voltage effects such devices are assumed to simply operate from ion wind. Okay, that's a cheap way out. If they want to say, now Townsend T. Brown, he discovered what I'll call the electrogravitic effect. And my understanding of it is different than most people right now. I followed the articles when it first came out in 1956 in Interavia, and that article was a tutorial on it. And it said that if you charge up a capacitor, while you're charging it, there's a gravitational field emitted perpendicular to the direction of the increasing charge, and only during the charging of it. And I have not seen any of the present schemes relating to electrogravitics that actually talk about the effect during the charging. And some of them work with the constant voltage there, and the only reason it does provide, because there's always leakage, and it's that leakage which provides. Now, I cannot say for sure that there's a electrogravitic effect, but if there is, that would be a definite way to achieve sustained acceleration and develop inertial propulsion. But most of it is poo-pooed, saying that they assume it to be ion wind, and that's bad. Now, back in '65, Norman Dean invented this thing, and it's some reciprocating elements, and they thought it would actually allow a space drive to be made. And I simply worked out the equations for where the center of mass of each of the moving parts was, and the center of mass never shifted. And so I knew immediately that that cannot work. And now, here is something. Now, I assume you were all briefed that you have to be able to read to attend this presentation. You have to read 10,000 words a minute. You have to, your eyes have to have a 10-to-1 zoom at least, and you have to have a photographic memory. Now, with those, now I'm happy that there are that many people with those talents. Now I'm going to show you 69 ways that don't work, and we're going to gloss over them, but they give names to them. From here I can hardly read it. Device for transforming kinetic energy. And but anyhow, now you got to pay attention close, zoom in on it, memorize it, and actually, if you go to the website and you click on one of these, it opens up that patent, and you can read all the patent claims and everything. So it's a good website, but there were 69 of them. Now I trust you all got that. So we'll move on a little. Now here's another claim. We're going to have something special on this one here. Robert Cook came up with the device in '72, and I corresponded with him, and I analyzed it. It's the center of mass never changes, and so it can't move, it can't work. However, now let me see what's okay. Okay, this is a picture of Townsend T. Brown. He discovered the electrogravitic effect. And I'm going to say a few words about David Hamill. In Canada, he's a guy, I'm not sure, I'm sure most of it is not true, but he said a spaceship came down and they escorted him inside of it, and they gave him a lot of data and released him, and they went away, and he went and built a spaceship according to now, he really did build something, And he says he built it in his garage, and it's in a 55-gallon drum. It's like 3 cone-shaped things with magnets on them, and so that the magnets are repelling each other, so that they can't stick together. And when you have 3 magnetic things floating, repelling each other, they cannot achieve a stable condition. And he said after a certain number of hours or days, something happened, and suddenly there's a plasma built up, and it got real cold inside, and the thing took off through the roof and never came back. And if there was a shred of truth to what he did, there's another possible approach to inertial propulsion, but it looks like it's not too reliable. And here's a craft that he supposedly built. And now this is a very interesting thing. John R. Searle, the SEG, the Searle Electric Generator, is the acronym. And he had some dreams when he was a child, and he published The Law of the Squares, and he said that all these secrets were revealed to him, and he actually built, he used a round ring with different magnets in it. The magnets looked a heck of a lot like this, only there's 3 rings of them, and it's very complex, but once they start turning, it can generate electricity. And he powered his house with it for several years, and they came and shut him down because he was stealing electricity or not paying for electricity that they suspected he was getting from the lines. And his wife turned against him, and they confiscated. He spent years building a real big one. And British Broadcasting Company, which is like CNN sort of, came, and every month they came and checked his progress. And if this is a picture, pictures are easy to fake. But now I'm still looking for, I haven't really gone into it that much, I'm looking for BBC or another photographer who actually took movies of something flying. Now if that's real and not faked, then that is a real answer also, a potential answer to inertial propulsion. I'd like to find, I'm contacting British Broadcasting Company to see if they still have a video of an actual flying spacecraft, because that means there is something. Now I'm going to mention another thing. He was very scientific, and he within the center of his ship, he put meters there and temperature sensors, and he noted that the temperature went way down. It got cold and freezing in there, and a plasma slowly built up around it. And after a certain point in time, the thing took off. And now here's the thing that I note in common about David Hamill and John R. Searle devices. They both got cold inside, and one way to get a cold is to, if there's a plasma shield around it, the plasma shield will not like, it'll create a vacuum inside it. If you create a vacuum, it's going to turn cold. And what happens if you have a balloon with something lighter than air? It's going to float. What happens if you had a balloon that was strong and you evacuated completely? It would go up until it reached the top of the atmosphere. Now, if you have a big enough plasma sphere with a vacuum inside it, it's going to turn cold. And the stories are, and these are real, that when his device took off, it took a batch of the earth with it. There was a little crater there, you know. It took half a ton of earth with it or something like that. And I am suggesting that this plasma sphere, which had a vacuum inside it, when it lifted up, it would suck up the dirt with it and go away. And it could be that the whole effect was simply like a floating balloon. It was a plasma sphere with the vacuum inside of it, and that could apply to both David Hamill and to John R. Searle. But John R. Searle, there's something real about it because it did generate electricity, and I'm trying to follow through on that. there's a good book. I encourage people to buy it and read it. Oh, by the way, I meant to say that last month's issue here of Extraordinary Technology, it's got some very good articles in it, and on page 45 is Nikola Tesla, the Lost Wizard. If you read this whole article, it'll break your heart. It'll almost make you start to cry, because if Nikola Tesla, he wasn't a good businessman, but he was a good scientist, and if he had been funded and the funding didn't renege on their promises, it would have been a different world today. It really, really would have. And so I encourage everyone to read page 45, starting the Nikola Tesla article. That's very good. Now here is an article that appeared in a magazine, and it's a center column with 2 hinge points and 2 rotors. And basically, if you torque that one round and round, those rotors will rise. And when they get up high enough, the party's over. You have to reset them. So you stop torquing it, you reset them, you poke them back down. And I'm going to call this process the Alex Jones process, because Eric Lathwaite, he was a genius. He invented the electric, the monorail type thing, and magnetic levitation. Suddenly, one day, you probably have all seen this film. He was labeled a heretic, Eric Lathwaite, because Alex Jones walked in and put something on the table and sped it up, and it lurched forward about 3 or 4 feet. And of course, you can say, well, it was touching the table or something, but it was real. And prior to that time, I know of no known mention of using gyroscopic effects to achieve movement. And so Alex Jones, he died about 97. It's kind of sad, but he is the father of what I'll call inertial propulsion in this respect. And Eric Lathwaite kind of stole it from him, never really gave him credit for it except that one clip in this BBC movie, which is called The Heretics. And so I'm going to label this the Alex Jones process, which is you torque something, you shift the center of mass up, and then you stop torquing, you reset it, and you repeat the process. There's Eric Lathwaite in his younger days, if you will. There's him in the middle of he'd take a spinning rotor and break it up into like a bicycle wheel with a little weight on each end so that it simulated a real rotor, but you could study the forces on each segment of the rotor, which is pretty tricky. Here's him in his older days and he died in the year 2000. I corresponded with him, and he said, come down and visit my lab anytime. And once I was on a trip back from the Czech Republic, I've been there 7 times, and I called his home. My brother Chuck and I, we were in London, and I called his home, and his wife answered, and Eric Lathwaite was out of town receiving a reward at another college or something like that. And so I never did get to actually visit him, but here, this is just a simple, they call it gyroscope. I'd call it a spinning rotor. That's kind of a definition of that term. Here's something else. I started to experiment with, instead of putting a constant torque on it, put an increasing torque on it and study its responses. I haven't had a chance to finish that analysis though. And now here's I'll call this the Alex Jones process. Here, again, this is the basic element. Now actually it has another element on this side too, so it's in balance. And over here you apply a little forcing torque on it and it starts to raise up. And you apply more forcing torque and it raises. And when you get to a practical limit, like it would be futile to go from 80 to 90 degrees because you're not gaining much altitude there. But if you go up to, in the case that I've designed, you go up to plus 30 and the reset stroke, you poke it back down. Now notice during here, the chassis never moves, but the center of mass of the rotor does raise up, and it has no inertia during that time. And so when you poke it back down, you're pushing against the housing, and you're poking, so the rotor actually drops down and the housing moves up, and you've gained a little bit of movement. We'll call that 1 inch in this case. In a tabletop model, we'll call that 1 inch. And so you repeat the cycle. You torque it, raise it up, reset it. And you can do that 100 times a second. You can do it 1,000 times a second. Depends on the limitations of your physical device. And that's what I call the basic IPU cycle for MMD, motion by mass displacement. That's the heart of everything, but it does not produce sustained acceleration. Now here's a chart from my last year's talk. If you put a power meter on it, you'll measure power like this, and the power, if you measure it by taking the voltage times the current without the angle between them, you'll get this much power out, and that's the apparent power. This much is real power, and the other is imaginary power, also called forget it. Anyhow, now my question is, this is well known in electrical engineering. It would be very hard to believe that there is not a corresponding analogy to it, because with the laws of electricity and the laws of mechanics, there's analogies all the way. And so I'm suggesting, okay, this doesn't change. The reactive, it's either imaginary or reactive, and those are standard terms in engineering. When I say imaginary, it's not a kook term. Now here's angular momentum, and there's the precession angular velocity. And this would be the real part of the angular momentum. If the spin velocity of the rotor is like this, the angular momentum will increase. And if there's actually a reactive component with it, this other equation defines a reactive component, and when you sum them two together by the square of the sum of the squares, this would be the term. Now, this is just a theory. I have not measured that, and it would be very difficult to measure in actual practice. Here's some more fundamentals. This is a large disk, and here it's being torqued, and it's going to precess. It's going to go round and round. Now, if it wasn't precessing, a point on the rim would move like this. But since it's precessing, that point's also going to move this way, and the resultant path that it takes would be this path, which is like the hypotenuse of those two paths. And it's been termed, this form of motion is called streptation. And the scientists believe that there's no real term like that, and they claim they understand precession, but they don't really. And so to me, that's a good term. I've been using it. And this just shows if something is precessing like this, and the rotor's rotating like this, and there's a forcing torque like this, it just shows the relationships. Now here's something, this is from a mechanical engineer's. This shows moments, bending moments. Just a beam by itself, if it goes far enough, it'll bend down. If you put a load on it, there's the equations. If you load it uniformly, and if you put a torque on the end, it'll bend like that. If you put a load in the middle, it'll bend like that, and so forth. And if you load it uniformly all the way and support it at both ends, if you put a torque on it like this, and those equations will come into play. I know you've never seen something like this, but if you have a, lever arm and a spinning rod on it, and it's precessing naturally. The rod, the rotor is heavy, and it's rotating like this. And how much torque does it take to carry the rod with it? Very, very little. The rod, the rotor is pulling the rod. On the other hand, in a forcing torque, you're forcing it like this. Now that's a heavy rotor, and so the bending moment in the horizontal plane is like 10 to the 7th times or 10 to the 8th times greater than it is for natural precession. And that will come into play when advanced devices are created. Let's see. Okay, here's a test bed that John and I built, and here's some tests we run on it. There's obviously a lever arm. Now the whole thing, there's obviously another equal part over here, and the rotor spinning, and if you torque it by turning that shaft, the rotor will rise up. And in order for it to rise up, it may pull up on this, and it may push up on this. And in order for it to rise up, this collar has to slide outward so it gets past the center point. And by locking this collar and that, by locking this and the top one, and either locking these or not locking them, you can run a lot of different tests. Now, ideally, if this raised up and it pushed that collar up against here and held it there, eureka, you've got sustained acceleration. And, whoops. Okay, here's another slightly variation on it, which we ran tests with it. And here's looking at it top down, the structure of it. And did we pass that video? Let's see. Yes, right now. Let me just. Okay, here's a video. Just watch it. It starts out at about plus 45 or 50 degrees, and watch what happens. It's actually rising up to 90 degrees, and then it collapses when it slows down. And now, yeah, replay that once more, John. Just punch it. Okay, I set it down there, and the center of gravity is low, and it's raising the center of gravity. Now, I defy anyone to explain how the center mass of that is raising itself up. You can shut that one off now, John. But the point is that the center of that rotor is being raised. Work is being done. And where's that energy coming from? Clearly, the energy comes from the kinetic energy in the flywheel. And so the flywheel is losing some energy while it's raising itself. And now I defy anyone to explain how that works. Let's see, where do I have that? I thought I had that description. Maybe that got okay. It looks like it isn't in the order that I had it in. I have an explanation of it. It would be titled Self-Rising Analysis. We won't dwell on it, but okay, there's the answer. Now, with your photographic memory and your speed reading, you should have no trouble retaining that. I'm not going to explain it, but if anyone feels they understand exactly how it happened, then I'd like them to come to me and tell me about it, because it's a pardon? See, your last chance to speed read it now. I can't give away all my secrets. Okay. Now, I compare natural precession and forced precession. I know it's getting late, so there's a big difference between the two, and I won't go into the subtleties between them, but they're totally different. Now here's a new equation. I've contacted two of the professors at California Institute of Technology, my old alma mater, to have them tell me the equation for this part of the equation multiplied by 1 is the angular momentum of a rotating disk if it's going around in circles. And I ask them if it's precessing at the same rate, what's the expression for the angular momentum of it? I have got no answers. I've contacted 3 PhDs from Massachusetts Institute of Technology. No answers. They pass the buck. They say, well, you should talk to this professor. That's in his department. And they say, well, you should talk to this professor. They will not give me an answer. And I derive this expression. That explains the angular momentum of that disk, whether it's not spinning at all or whether it's spinning in full precession. The angular momentum starts out here and then it drops off to 0 angular momentum. Now actually, if you have a physical device, that's 0 angular momentum for the active mass. The shaft that's holding it, unless it's turning also, and the housing and all that, there's angular momentum associated with that. And so now here's centrifugal force. If it's going round and round precessing, normally that rotor wants to be pulled outward like on a merry-go-round. And during precession, there is no centrifugal force except associated with the lever arm that holds it or any gimbals that hold it. And so here's a similar expression. The centrifugal force is this term, but the term that considers the speed of the rotor is here. And that both these, the expressions for the angular momentum and the centrifugal force meet the boundary condition of full angular momentum at 0 spin velocity and 0 force at full precession or high speed. This was the one that we... Now maximum velocity. Next year, John and I hope to have a little device, maybe it'll look like a briefcase or a lunch bucket, and have it move across at a certain velocity. Maybe its velocity will be only 1 inch per second or something like that, but it'll be a prototype built with minimum dollars, and we're going to build something like that this coming year. And it'll have the little precession reset cycle going continuously inside of it, but it won't produce sustained acceleration, and it'll have a maximum velocity. Now I've just let's see. Okay, I had the equation for the maximum velocity, but that's an equation for the maximum velocity. Now, if you scale it up or down, I've made a breakthrough. Which I won't fully disclose, but these parameters here, if you study it, the maximum velocity varies as the 5th power of a certain variable. And if you go down to nanotechnology, use nanotubes, normally the round rotor, if you make that smaller and smaller and use a heavier lever arm so that the rotor is the lever arm itself, I call that a rolling pin rotor, a rolling pin roller. And using now with nanotubes, nanotubes are much stronger than steel. They're elastic, and you can put them in form of tubes, and you can have multiple layers. Okay, if you have a rolling pin rotor made out of nanotubes and use the right dimensions, the right length and the right diameter, you can get up to 1,000 miles an hour easily. And now I'm also saying that, like the car companies, they'll spend millions or even billions of dollars on car designs. If we use these principles here, we could build a Lamborghini that'd go 100 miles an hour in 1 second. The only reason it takes 1 second is because it has to drag along the frame. It has to get the frame up to speed. Because the active mass itself, if it didn't have to drag something with it, would get up there in 0 time. Now, physically that's impossible because there's always some passive mass associated with it. But if I were given $1 billion, I could build a Lamborghini and it'd have wheels. The wheels would not be used for traction. There'd be no connection between the motor and the wheels. The wheels would be to keep it off the ground and to steer it. And that could actually be done, but that would not produce sustained acceleration. Once you get to the maximum velocity, it's done with. However, if you shut the IPU off, the car stops instantly also. If it gets up to full speed, if it's a big thing, it gets up to full speed in 1 second, it'll stop in 1 second. And the bottom line there is that there's a lot of stories about flying saucers and UFOs that go at a high speed and suddenly turn a sharp corner. Well, that's exactly the type of thing that inertial propulsion, just only motion by mass displacement, can do, not even sustained acceleration. And whether it's in the air, now the thing I'm talking about can't be in the air because it has to levitate or something. I'm talking about ground-based objects so far. And a Lamborghini could turn a square corner at 100 miles an hour. And so this does indicate that if there are such things as flying saucers, they're using some form of inertial propulsion. That has to be obvious. And there's a lot of work to do. I'm getting a little bit old, and you know, a lot of inventors, they like to keep things secret. They're afraid of someone's going to get it and go steal it and make $1 billion and leave them without a dime, and they're going to die busted and heartbroken. And on the other hand, you've heard people here say that they want to publish everything, get it out to the world, get as much people building it. And I'm approaching that point myself because there's a lot of, if I had the money, I would hire a PhD in math, a PhD in physics, a PhD in mechanical engineering, statics and dynamics, a PhD in computer science, and a good machinist. And John's a good machinist besides being good in areas of physics. But I don't have that kind of money, so I'm asking for volunteers from this audience here. I want to, and after this is over, I want you to line up and come to me and volunteer for certain tasks on that. And summary and future plans. We've run tests that absolutely prove MMD is possible. We'll demonstrate that next year. We ran tests to demonstrate sustained acceleration. The tests were not conclusive. Our prototype had several known problems. The results are encouraging, however, but we do not want to pull what I'll call another Eric Lathwaite or Pons and Fleischmann with a premature announcement. Now, actually, Pons and Fleischmann, it's the college that announced it for political reasons, so it isn't really their fault. And Eric Lathwaite, he didn't claim he had anti-gravity. He wanted to show the Royal Institution in London something very exciting, and they called him, they said, you're violating Newton's laws, and they called him a heretic, and they didn't publish his paper. And next year, we want to demonstrate MMD. 2 years from now, I'd like to announce that we're able to demonstrate in a laboratory sustained acceleration. Maybe 3 years from now, we'll have a little device. Maybe it won't be strong enough to go against gravity, but it'll produce some sustained acceleration. And now we have 10 seconds for question and answers.
Okay, time is short. We've got about 6 minutes for question and answers. We're going to bump the afternoon schedule off exactly 30 minutes. The afternoon, all of the afternoon times in your brochure there, and are going to be bumped back 30 minutes. And we'll commence the Q&A after one other quick announcement. Larry Ojai and some others are going to have the water fuel torch outside, and they'll weld a brick, or if you can find one, and they're going to be doing that during lunch. So that during lunch you'll have some show and tell opportunities also with Larry. So we're not going to start at 1 o'clock like we were originally planning. It'll be 1:30. Okay. Now, questions for Harvey? We got about 5 minutes. If you want to come to the left staircase.
Remember, all the volunteers see me out in the hall afterward.
On the
Is it on? Here. Yeah, go ahead.
on the gyroscope
Scared 'em?
that on the gyroscope that processed and stood up, if you stopped it from processing by just put your finger on the gyroscope that processed and then stood up, would it still stood up or just would it have stayed at that angle?
I'm hard of hearing. Could you repeat the question?
On the gyroscope that was processing and then stood up, if you stopped it from processing by just putting your finger, it would not have stood up. Is that not correct?
That's right.
So the precession, the rotation due to the friction of the shaft is what caused it to actually stand up.
No, that's not right.
But you can stop it by precessing.
You stop it by stopping the forcing torque.
Right.
And if it's in gravity, it'll start falling. If it's on a roadbed, it'll stop its forward velocity.
Right. But okay.
Okay, we have one more announcement before everybody gets out of the room, and you may need to pass this on. We have another session that's getting inserted late in the afternoon. The way the schedule's been going, this means it'll be at about 5:30. What they've decided to do is we've got the presenter schedule now for the
Okay, you are George?
the so-called Joe Cell seminar. It's been converted.